So this is the second lecture, and we'll finish up chapter 16. So first, let's talk about the biosynthesis of triacylglycerols. So that's this right here, triacylglycerol. So we have a glycerol backbone and 3 fatty acid chains. And if you remember from biochemistry, these 3 fatty acids can be any fatty acid, although in mammalian cells there are some that are more common than others. So when we have fatty acids that are synthesized from the reactions that were described in the previous lecture, or if you ingest fatty acids, there's really 2 things that can happen to all of these fatty acids. We can either incorporate them into triacylglycerols, and this is a storage form of metabolic energy, so these triacylglycerols can then be hydrolyzed to release those free fatty acids when fuel supplies run low, or we can use free fatty acids as precursors of phospholipids, and so we'll talk about that next. So here we're really just going to talk about the triacylglycerols. So we can synthesize and store large quantities of these triacylglycerols to use as fuel. Although there are limits in the amount of glycogen that can be stored, we have unlimited amounts of triacylglycerols, as we've discussed in a previous lecture. So let's look at the process of triacylglycerol storage. So the first thing we need is a glycerol backbone, and that can come from a variety of sources, but one source is dihydroxyacetone phosphate, can be used to give us glycerol 3-phosphate. Glycerol we can get from a variety of pathways, one of which, if you remember, is the fructose metabolic pathway in the liver. That can give us glycerol. In either case, we could either use glycerol or dihydroxyacetone phosphate to give us glycerol 3-phosphate, which is a precursor for that lipid backbone. Once we have glycerol 3-phosphate, we have 2 fatty acids come in and are attached at these hydroxyls, the 2 that do not have the phosphate group, so carbon 1 and carbon 2, to give us phosphatidic acid. That phosphatidic acid, then we can hydrolyze the phosphate and put on that last fatty acid group. This phosphatidic acid is important because it can become it is a central intermediate in lipid biosynthesis, and so from this point when we have phosphatidic acid, we can either convert into our diacylglycerol and then our triacylglycerol, or we can take this phosphatidic acid and use it as a precursor for a glycerophospholipid. Now, this synthesis of triacylglycerols is hormone regulated, so that we synthesize fatty acids when we have excess fuel, and we don't synthesize fatty acids when we are fuel deprived. So next, let's talk about some of these glycerophospholipids. So glycerophospholipids, these are key components of cell membranes, also involved in signaling pathways. So if a cell is rapidly dividing, then it would need new membrane lipids, and so we would trigger synthesis of some of the glycerophospholipids and also the sphingolipids, depending on which cell type it was. The eicosanoids aren't actually a derivative of a triacylglycerol, but they are also formed from a fatty acid precursor, so they kind of fall within this groups of other things we can synthesize from fatty acids. So this is showing you a glycerophospholipid where we have our 2 fatty acid chains. Remember that we attached to form phosphatidic acid, and then instead of cleaving off this phosphate group, instead it stays or is modified slightly with a hydrophilic head group. Glycerophospholipids are synthesized in similar ways in eukaryotes and prokaryotes. There are a few differences if you look at eukaryotic only, and that mainly comes from the source of the phosphatidic acid. But we have glycerol 3-phosphate to give us phosphatidic acid, attachment of two acyl-CoAs. Remember that if we want to make triacylglycerol, this synthesis will diverge there, but if we want to make a diacylglycerol and then some of our phosphatidic acid, some of our glycerose phospholipids, this is where synthesis will converge. So that head group that can be attached, that phospholipid head group, can be serine, ethanolamine, choline. Then we also have other molecules that we can make from our diacylglycerol, so our phosphatidylglycerol and our cardiolipin. So before phosphatidic acid can serve as a precursor for all of our phospholipids, we first have to activate it to form CDP diacylglycerol. So CDP diacylglycerol is formed when CTP is used to attach a CMP group onto our glycerol backbone that already has our two fatty acids. Because there is already a phosphate group attached, remember here, so this becomes CDP diacylglycerol. So there's two acyl groups, so diacylglycerol, CDP. Alright. The pyrophosphate that is released is hydrolyzed into two inorganic phosphates, and remember, anytime we have a reaction that's coupled with the hydrolysis of pyrophosphate, that makes the overall process irreversible. Now that we have this CDP diacylglycerol, now we have a good attachment point for any of the head groups to make our various phospholipids. We can also synthesize a class of lipids called sphingolipids, and these can then be attached to the diacylglycerol. So sphingolipid synthesis has four different stages. The first, which is the synthesis of our 18-carbon sphingosine from palmityl-CoA and serine. Then we attach a fatty acid through an amide linkage to yield our N-acyl sphingosine, which is also called ceramide. And then we attach a head group to produce a sphingolipid, either cerebroside or sphingomyelin. So here's sphingomyelin, cerebroside. So our attachment group determines which lipid we get. And this is just an example of lipid synthesis. So we're not going to go through all the different types of lipids. Primarily, you want to focus on the role of the diacylglycerol and phosphatidic acid as a precursor for synthesis of some of these lipids. So next we're going to turn to something that I think we're a little more familiar with, is steroids. So steroids are built of one or more isoprene units. All steroids have this four-ring structure that you should be fairly familiar with. One of the most common steroids I think we talk about is cholesterol. And so we'll talk about the synthesis of cholesterol. Now cholesterol, even though we hear about cholesterol because of its relationship to cardiovascular disease, cholesterol also has a really important role as a component of cell membranes. Cholesterol gives membranes a certain amount of rigidity, which is necessary to protect the cell. Okay, now let's take a closer look at cholesterol synthesis. We start with acetyl-CoA, two acetyl-CoAs, in fact, that are condensed to form acetoacetyl-CoA. This pathway is outlined in your book. Through two additional steps, we produce mevalonate, which is the precursor for your isoprene units. Cholesterol synthesis is regulated at the step that produces mevalonate, catalyzed by HMG-CoA reductase. Inhibition of this step will inhibit cholesterol synthesis. Once we have the isoprene units, cholesterol synthesis continues. Now, if you look at the synthesis of mevalonate from acetyl-CoA, you will notice, hopefully, that the pathway looks very similar to the synthesis of ketone bodies. However, ketone bodies are synthesized in the mitochondria, and mevalonate is synthesized in the cytosol. So that's the main difference between those two pathways. Otherwise, the enzymes are very similar. Once we have mevalonate, then we form our isoprene units, which are condensed into squalene and then on into cholesterol through a number of different steps that we will not get into at this point. This is just a closer look at the condensation of your isoprene units into squalene. Once squalene folds, then it forms into cholesterol, but can also form into a number of other molecules. So humans derive all of their steroid hormones from cholesterol, and there are two classes that are synthesized in the cortex of the adrenal gland, which are mineralocorticoids, which control the reabsorption of inorganic ions by the kidney, and glucocorticoids, which help regulate gluconeogenesis and reduce the inflammatory response. Sex hormones are produced in male and female gonads and placenta, which includes progesterone and our androgens, testosterone, estradiol, or one of our estrogens. So steroid hormones are effective at very low concentrations, so we only synthesize very small quantities of these. So even though they are synthesized from cholesterol, we use up very little cholesterol to synthesize all of these different hormones. To synthesize the steroid hormones from cholesterol, we have to remove some or all of the carbons from the side chain that's at C17 of the D ring. And so this takes place in the mitochondria of whatever tissue is synthesizing that particular steroid hormone. And so what is formed is this intermediate pregnenolone, which is used to form all of our different steroid hormones. Now, along with the steroid hormones, it can also be used to, or cholesterol intermediates can also be used to synthesize several other important biomolecules. So isopentyl pyrophosphate is an intermediate in cholesterol synthesis and is also an activated precursor of a large amount of biomolecules, which include vitamins A, E, and K. In plants, this can also be used to produce keratin and part of the phytol chain of chlorophyll, along with a vast amount of other essential oils and hormones, etc., etc., etc. So this is just showing you synthesis or some of the molecules that can be synthesized from that isopentyl pyrophosphate precursor. So finally, we can look at the synthesis of our eicosanoids, and this is a family of very potent biological signaling molecules that act as short-range messengers. They only affect tissues that are very near the cells that produce them, so they don't travel long distances through the body. They're produced in response to hormone or other stimuli, and they are synthesized from our 20-carbon polyunsaturated fatty acids. So some of those essential fatty acids that we cannot synthesize, we must ingest through our diet and then use them to synthesize arachidonic acid, which is the precursor for many of these signaling molecules. So the eicosanoids contain molecules such as prostaglandins. Those are involved in inflammation. So this note here, aspirin inhibits some of the enzymes that produce prostaglandins, which is why it has an anti-inflammatory effect. So again, this is why our essential fatty acids are so essential. Without them, we would not be able to make a number of our eicosanoids, which can control a wide range of biological processes. All right, So that is the end of fatty acid synthesis. Again, these last couple slides are not real detail heavy because we just want a little bit of an overview of all the different types of molecules that can be made once fatty acid synthesis has been completed. All the different types of lipids that we can make from those fatty acids. All right, so I will see you in class on Monday, and we'll have our PBL and explore fatty acid synthesis a little bit more.